Okay, so we're going to continue the discussion of the limit as x goes to infinity or negative infinity. So what we're really looking for, just like we saw in the previous video, is what happens as x goes out to the left and to the right on a function. So what we're going to be discovering here is the horizontal asymptotes for each of these problems. Just like in the 1 over x example, as x approached infinity and negative infinity, we approached the horizontal asymptote. The same thing is what we're looking for here, because horizontal asymptotes, by definition, define what happens as x approaches extreme values, what the ends of your graph do. Another word for that is the end behavior. All right, so let's try and apply what we discussed about the 1 over x to these problems. So we're going to use all the limit tools that we've already talked about. So you're going to review a lot of those. So take advantage of this time to review. All right, limit as x goes to infinity. How do we take the limit of two terms? If you recall, we can break it up and take the limit of each term separately. So this is the limit as x goes to infinity of 2 minus the limit as x goes to infinity of 12 over x. Okay, break it up. So what do you know about the limit of 2? This is a constant. So the limit of a constant we've talked about. It doesn't matter what x is approaching. If you have a constant, the limit is the constant itself. Constant means it doesn't change. So no matter what x is approaching, it will always be the same value. Minus. All right, what about this one? Now you have an option of doing something with this 12. This 12 is a constant multiple. You can write it as 12 times 1 over x if you wanted here, instead of 12 over x. So that 12 could actually be pulled out. Or you can use the shortcut that I showed you, that if you have a finite number and the denominator goes to infinity, the denominator blows up, then what happens to this fraction overall? Finite number divided by infinity goes to who? Goes to 0. So once you've taken your limits, then you just work it out. 2 minus 0 is 2. This would be the horizontal asymptote, or the limit as x goes to positive infinity for this function. Let's try another one. So in this case, we have x going to negative infinity. It's the same basic rules apply to both. It's just the directionality that we're coming from is a little bit different. But you're still going to go to 0 if you have a finite number divided by x. Now, this time, though, we have something weird. We have x cubed. What are we going to do with that? Well, let's think about this. There's a couple of ways we can deal with this. One way is to think through the process. If we take a negative number and we cube it, what's going to happen to that negative number? It's still going to be negative, right? Okay, so we're still going to a negative in the denominator. If we take infinity and we cube it, what's going to happen to the infinity? Infinity times infinity times infinity. What is that? If you take a big number and you put a power on it, it's going to become even bigger. So this denominator is actually going to negative infinity, but even faster. It's speeding up the process. But you're still going to the same value. So that's one argument we could have, and we could say that this is going to be 17 divided by negative infinity. And what happens if you have a finite number divided by infinity? The whole thing goes to 0. There you go. If you want, you could use the limit rules and break this up. You could pull the 17 out of your limit. So this would be a constant multiple coming out. And then we could break up the rest of this. So we have 1 over x cubed. Let's see. We have a limit rule about breaking up a product and breaking up a quotient. So we could bring the limit inside. We can have, all right, so 17 is still out there. We can take the limit of each fraction separately if I break it up. So we could do, instead of 1 over x cubed, 1 over x times 1 over x times 1 over x. We could take the limit of each one separately. We could do that as long as the limit exists. So the limit of 1 over x would be 0. Then 1 over x would be 0. So all these would be 0. So what's 17 times 0 times 0 times 0? It's still going to be 0. So that's two different ways to look at that problem. Okay, so you can use the argument of what's happening to the infinity. It's getting bigger even faster, so it's still going to infinity. Or you can use this argument of breaking it up and using your limit rules. Whoa, what happened? Okay, on the next problem, I want you to notice that x is still going to infinity. This case, though, x is not only in the denominator, it's also in the numerator. Now that can cause us problems. Let's just try and plug it in and see if we can figure out by plugging in what the answer would be. So hypothetically, if you were to take infinity and plug it in here, infinity squared, we just kind of talked about that. If you square infinity, it's just going to be even bigger. So that's still infinity times 5. If you take a big number and multiply by 5, so that's infinity, all of that. Okay. What about 8 times infinity? It's also infinity. So we have infinity plus infinity. If you take a big number and add more big number, that's still a huge number. If you take away 3, so if you go up to Donald Trump and you say, I want $3. So you have all his money minus 3. What is he still going to have? Tons of money. So this is still going to be infinity. So the numerator for this is infinity. So this is just a numerical argument of what's happening. On the bottom, x squared again. If you take infinity and square it, it's still infinity. If you multiply by 3, it's still infinity. Plus 2. So if you go to Donald Trump and hand him $2, he's going to laugh, but you never know. He's still going to have infinity, a very large number. What is infinity divided by infinity? Do not tell me that this is 1. That is not correct. You cannot determine what this is. This is like trying to compare Trump to Gates. Do you agree they both have a ton of money? Absolutely. But if you go do some research, you'll find out that one has more money than the other. To us, it just seems like a lot. They're rich. That's all we care about. But one has more than the other. So one of these infinities is going to outweigh the other. So that's what your job is going to be here, to determine which one of the infinities is larger. So to do that, we're going to learn an algebra trick here. So this was an interesting discussion, but this is not how you're going to approach this problem. Let me show you what you're going to do. I'm actually going to erase this so that I can have a clean slate. There we go. All right, so the trick is this. You're going to multiply top and bottom by 1 over the highest power of x in the denominator. So in this case, that's x squared. Always use the power of x in the denominator. Let me write that down. Highest power of x in the denominator. Whatever you do to the top, you do the same thing to the bottom. By doing this, we're not changing the value of our problem because this is equivalent to 1. We do top and bottom the same thing. We're not changing the value of the fraction. We're simply doing algebraic manipulation. But I want you to see what happens when we do this. So we still have our limit notation. Don't forget your notation. But our fraction, we're going to distribute the 1 over x squared to every single term up top and to every single term on the bottom. So can you work with me here? Pause the video. I want you to try it. Make sure you understand the algebra here, and then we'll talk about the answer. All right, so if you paused it, great. If not, go do it. So 5x squared divided by x squared, that leaves you with just a 5. 8x over x squared. So one of the x's will cancel, and you're going to be left with one of the x's on the bottom. Be careful to keep track of things. Minus 3 times 1 over x squared would be minus 3 over x squared. On the bottom, 3x squared divided by x squared would be 3 plus 2 divided by x squared. Okay, so now if you look at this problem, we can use our limit laws and we can do the top and the bottom separately, the numerator and the denominator of the big fraction. And then inside the numerator, we can do each term separately. The denominator, same thing, you do each term separately. So let's find the limit of each term individually as x goes to infinity, and then we're going to put it all together. All right, what is the limit of the constant 5? Well, that's still going to be 5. That does not change. He's a constant. So 5 plus. What is 8 over x going to do as x goes to infinity? You have a finite number divided by infinity. So this whole fraction goes to 0, just like in the previous two problems. Finite number divided by infinity goes to 0. Same thing with 3 over x squared. Finite number divided by infinity, or negative infinity, either way, this goes to 0. So on top we have 5 plus 0 plus 0. On the bottom, again, we have a constant. So what's the limit of a constant? A constant plus, as x goes to infinity, what is this fraction going to do? Finite number divided by infinity, even infinity squared, same thing, goes to 0. So the limit of this fraction is 5 over 3. Okay? Now, some of you might be saying, I saw that at the beginning. That's great. But I expect you to show the work, to take the limit. I want to see the process. After this test, you can do shortcuts to find these. Remember, what we're really finding here is the horizontal asymptote. So this is the horizontal asymptote of the original function. In algebra, pre-calculus, other courses, you might have learned some tricks. I will review those tricks, but right now I want to finish going through the 3 examples, and then you can probably tell me what the tricks are. All right, let me try another one here. So again, we have x in the numerator and the denominator. X is going to, this time, negative infinity, but still giving me the same discussion. We can't just plug in infinity because we're going to have infinity over infinity. Maybe negatives included, but still, infinity over infinity is something that's undefined. We cannot talk about that. So what we're going to do is we're going to apply the rule that we just talked about. We're going to multiply top and bottom by the same thing. 1 over, which power do we pick? It's right there on the screen. Highest power of x in the denominator. In this case, that's x cubed. So 1 over x cubed, top and bottom. And let's see what happens. So we're going to distribute 1 over x cubed to every term on top, and we're going to distribute it to every term on the bottom. So limit as x goes to negative infinity, 11x over x cubed. I can reduce that. So it's 11 over x squared plus 2 over x cubed. That one I can't reduce. Divided by, on the bottom, 2x cubed divided by x cubed. That's 2. Minus 1 over x cubed. Same thing as before. And I'll take the limit of each individual term and then just put them all together. So as x goes to negative infinity, all of these fractions, number divided by infinity, number divided by infinity, number divided by infinity, they all go to 0. And you end up with just 0 plus 0 over 2 minus 0. Work it out. 0 over 2. Okay, what's 0 divided by a number? Remember, this way, the answer is 0. Later on, we're going to have it the other way around sometimes, which is going to be a problem, and you're going to have to do some more work. So just be careful that you acknowledge that. So what we found here is the horizontal asymptote for this function. Okay, so I'm going to pause the video here. I'm going to do a separate video, and we'll continue this discussion in that video.